Now that we're familiar with Euler's phi function, we want to find out some more properties of this interesting and important function. And as we do so, we realize that Euler's phi function is what is called multiplicative. That's an idea where basically products under certain circumstances can be moved into and out of the function. And so what we're going to do then is we're going to also investigate multiplicative functions. Let's take a look at what they are. So, an arithmetic function is just a function that is defined for all positive integers. And an arithmetic function will be called multiplicative if and only if when the greatest common divisor of m and n being 1 implies that the value of the function at the product m times n is equal to f of m times f of n. So just like I said, under certain circumstances, namely that the greatest common divisor of the two factors is 1, we have that the value of the function at the product is equal to the product of the values of the function. A function is called completely multiplicative if and only if we have this property for all m and n. So if for all m and n we have that f of m n is equal to f of m times f of n, that is substantially more rare to occur, and we're not going to see it very often here. So in this presentation we will see that Euler's phi function is multiplicative. That's that section. We will consider the sum and number of divisor functions, which both are multiplicative. That's why they're in this presentation. And we will explore the relationship between a multiplicative function f and its summary function, which is capital F of n being the sum over all divisors of n of the value of the function lowercase f at the divisor d, and that ultimately connects to Möbius inversion, and perfect numbers and Mersenne prime numbers are somewhere in between there. They're a notion that is better investigated using multiplicative functions. Okay, so first, quick little theorem. If a function is multiplicative, and if the prime factorization is the product pj to the aj for n, well then f of n is just the product of the f of pj to the aj, and that ought to make sense because after all the primes have greatest common divisor 1, so the product should move out. And the proof is in fact a quick induction on the number of factors. The base step for s is trivial. Okay, that should be the, not then, or then the base step. Well, I don't think that's too crucial right now. The induction step from s to s plus 1 is that we let n be have a prime factorization with s plus 1 factors. Well, then f of n is f of the prime factorization, and we can split off the last factor. So this is f of product of the first s factors times the last factor. And because the prime number ps plus 1 is different from all the other pj, we have that the greatest common divisor here is 1. And so that means that this is f of product of the first s prime factors with their powers times f of ps plus 1 to as plus 1. Then, of course, we use the induction hypothesis because we can pull the function into the shorter product, and that means that f of n really is the product j equals 1 to s plus 1 f of pj to the aj as is seen here. And that's already it. So one of the nice things about multiplicative functions is that once we know what these functions do on powers of prime numbers, we pretty much know what those functions do overall, as long as we can factor the input. So now, a quick theorem that connects to the phi function, and that is that a positive integer is a prime number if and only if phi of p is p minus 1. That shouldn't be too bad, because after all, the phi function gives us the number of all numbers smaller than p that are relatively prime with p, so that sounds like it ought to be the right thing, and it shouldn't be too hard. So, left to right, suppose our number is prime. Well, if p is prime, then for every number between 1 and p minus 1, we have that the greatest common divisor of the number and p is 1, and that means phi of p is p minus 1. The other direction should be similarly easy. If phi of p is p minus 1, well, that means that the greatest common divisor of a and p is 1 for all integers from 1 to p minus 1, and that means that p is prime because it doesn't have any divisors strictly smaller than p except 1. And that's it for that one. The next theorem is about the Euler phi function at the power of a prime number. So let p be a prime number and a positive integer. then phi of p to the a is p to the a minus p to the a minus 1. And the proof is a counting argument, namely, a number that is between 1 and p minus 1, p to the a minus 1 could also go with p to the a because we're talking about greatest common divisor between the number and p to the a being 1. Well, that's the case if and only if x is not if p is not a prime factor of x. Well, there are p to the a over p equals p to the a minus 1, multiples of p in the set 1 through p to the a. So we really want to focus on p to the a, but the statements remain true. And, well, that means, of course, that these are the numbers in the set 1 through p to the a, and p to the a is one of them. These are the numbers that would have to be excluded from the counting of numbers that are relatively prime with p to the a, and that means from these p to the a numbers, we have to take p to the a minus 1 numbers out. And we can see why we didn't want to go to p to the a minus 1, because the exclusion would take p to the a out anyway, and in this fashion, the counting is easier because we don't have to keep track of extra plus minus 1s. Okay, what now? Still talk about the phi function. Yeah, here is the theorem that says that the phi function is multiplicative. So we want to prove that if we have two numbers m and n whose greatest common divisor is 1, we want to prove that then phi of m times n is phi of m times phi of n. And the proof is the following. We will split up the set of numbers from 1 through m times n, and we will split it up by remainders. So the set of numbers from 1 through m times n is the union over all remainders between 1 and m, so we're going to not use remainders 0, we're going to replace those with remainders m. So it's the union of over all remainders between 1 and m of numbers of the form d times m plus r, where d is between 0 and n minus 1. So this starts with d equals 0, r equals 1, so it starts at 1. And when d is n minus 1, and r is m, then we actually also capture m, and we capture all the numbers in between. Well, if the greatest common divisor of m and r is b not equal 1, well then for all numbers x in this set where the remainder is r, we have that the greatest common divisor of x and m times n is greater or equal than b, and that's greater than 1. And that is because any number in here, greatest common divisor between a number dm plus r and m, will be at least the greatest common divisor of m and r, will be at least the greatest common divisor of m and r, because anything that divides those two will also divide m and n, and b does that already. So that means these are numbers that are not counted by Euler's phi function, and so that means that certain remainders are simply excluded, namely all the remainders where the greatest common divisor between m and r is greater than 1. If the greatest common divisor of m and r is 1, well then again we look now at all the elements in this set dm plus r, where d goes from 0 to n minus 1, and for all these numbers we have that the greatest common divisor of y and m is 1, and that is because otherwise the greatest common divisor of r and m would be greater than 1. Yeah, sure. And now we would recall that for fixed r, because we assume that the greatest common divisor of m and n is 1, we have that this set here is a complete set of non-negative residues modulo n, because what do we have? The d's are a complete set of non-negative residues modulo n, and we have a result proved earlier which says that if we multiply that with a number that has greatest common divisor 1 with n, and we add another number, we retain a complete set of non-negative residues modulo n. And so that means exactly phi of n elements of this set dm plus rd from 0 to n minus 1, exactly phi of n of these elements satisfy that the greatest common divisor of y and n is 1. And because the greatest common divisor of y and n is 1, and the greatest common divisor of y and m is 1, every one of these elements then satisfies that the greatest common divisor of y and m times n is 1. And that summarizes it already, because there are phi of m sets among these sets that we have up here that contain elements whose greatest common divisor with mn could be 1, and each of those sets contains exactly phi of n such elements, so that means that the total number of elements in this set that have greatest common divisor 1 with m times n is phi of m times phi of n, which is exactly what is claimed up here. And so, yeah, that's what we're saying, and that ends the proof. All right, so basically what that means is that if we have the prime factorization of a number n given, well, then we can write down phi of n as a product directly, and let's see, the one that we're actually going to prove is this one, and that basically says that, well, we can take the product out, and we know that phi of pj to the aj is pj to the aj minus pj to the aj minus 1, and if you factor pj to the aj minus 1 out, you get this, so that works. And, well, if I were to factor another pj out of here, I would get 1 over 1 minus 1 over pj, but then I could split up the product, and the product of the pj to the aj would be this n out front here, so this is just arithmetic. Okay, so how do we prove that? Well, probably induction. And the base step is an earlier theorem that we have just shown. And so the induction step s to s plus 1 shouldn't be that bad because, well, we take phi of the prime factorization, we split off the last factor, we use multiplicativity because ps plus 1 has greatest common divisor 1 with the remaining product here, so this is phi of the product of the first s prime powers times phi of the last prime power. Then we use the induction hypothesis, which is that phi of this product is actually the product pj to the aj minus 1 times pj minus 1. And we also use the theorem, and we split off the ps plus 1 to the as plus 1 minus 1 times ps plus 1 minus 1. And now that is written, after we combine the products, it is written exactly as it should be in the statement there. And that's already that. So, if we have an integer that is greater than 2, then from this formula we can claim or prove that phi of n is an even number. And, well, we look at the prime factorization of our number, and there are two. Well, then we know that phi of n is the product j equals 1 to s pj to the aj minus 1 pj times pj minus 1. And there are two possibilities, namely, n could have an odd prime factor pj, and if that happens, well, then the product for phi of n has the even factor pj minus 1, and so phi of n is even. And the other possibility is that n has no odd prime factors, and that means that n is 2 to the k, and because n was greater than 2, that would mean that 2 to the k minus 1 is greater or equal than 2, and that's a factor, namely this factor here, in the product for phi of n. So either way, as soon as n is greater than 2, phi of n is an even number. We can also talk about what we will ultimately call the summation function, or the summative function, I'm not quite sure on the wording right now, of the Euler phi function. And what can be proved, and what we will prove, is that if you've got a positive integer n, and you sum over all the divisors d of n, you sum the function phi of d, you retain n. And again, that sounds like it ought to be okay, because somehow those numbers ought to capture all the numbers below n. Well, not really, because the divisors are smaller than n, and so certain numbers such as n minus 1 would not be in the sets that we're using to compute these phi of d. So it's not entirely obvious, but we'll go through the proof here. So basically, for each divisor d of n, we will let cd be the number of all numbers m between 1 and n minus 1, so that the greatest common divisor of n and m is d. Okay? And what we know then is that the set of all numbers from 1 through n is the union of all divisors d of n c sub d. And that is all right, because if a set is used twice, well, and no set is being used twice because we've got a divisor here. And we're looking at greatest common divisors. All right, so let's see. Take any number smaller than n. That would be a number m. Yeah, sure. And that number m has a greatest common divisor d within, and so it's in one of the CDs, right? And if you take a number in these sets c sub d, well, then of course it's a number between 1 and n minus 1, so that's in here, and I would say that probably c sub n, that's going to be just singleton n. So we probably have to assume here that c sub n is singleton n. And so, well, or this is just a set 1 through n minus 1. I think that should be the set 1 through n minus 1 here. Okay, so now let's note that c sub d is the set of all numbers between 1 and n minus 1, so that m is x times d, where x is a number between 1 and n over d, and the greatest common divisor of n over d and x is 1. And that means that the number of elements of c sub d is actually phi of n over d. And so that means that n is the sum of all the d dividing in c sub cd absolute value, which is the sum over all d divides in phi of n over d. And that's the same as the sum over all d divides in phi over d itself, because whether we sum over the n over d's or whether we sum over the d's, when d is a divisor of n, then n over d is a divisor also. And I think what we really need to say here is that phi of n is a separate, I think we simply have to go up to n here. Hang on just a second. Yes, indeed, there was a little typo on these slides. The sets c sub d consist of all the numbers m between 1 and n who have greatest common divisor d with n. And that certainly means that the sets c sub d are pairwise disjoint because the greatest common divisor is unique. It also means that the set from 1 through n is the union over all the CDs, because every element in here is in one of the CDs, namely the d that is the greatest common divisor between it and n. And that then, and now the rest is okay. Here we're looking at the set CD of all the, that's the set of all numbers between 1 and n, so that m is d times x, where the greatest common divisor between x and n over d is 1. And that would then mean that the c sub d's have phi of n over d elements, and the computation stays as it was. Okay, so as an example, if we were to find all solutions of the equation phi of n equals 7, well then, because 7 is not even and phi of 2 is 1, there is no solution of that. And for even right-hand sides, the argument does get more complicated, and that is something that I'll leave to you. Okay, so now we're going to talk about the sum and number of divisor functions. The sum of divisors function sigma assigns to every positive integer the sum sigma of n of all its divisors, including 1. And the number of divisors function tau assigns to every positive integer the number tau of n of all its divisors, including 1. And when we talk about divisors here, we certainly only mean positive divisors, so it would be the numbers between 1 and n that can be used as divisors here. So basically what that means is that sigma of n is the sum over all d divides n of d, and tau of n is the sum over all d divides n of 1, built very similarly to what we have seen in this formula for the Euler phi function. And that means that both sigma and tau are what is called summary functions, which I don't think we have to find them yet. Okay. So the summary function, basically the summary function is what you get when you take a function and function at n is the sum over all divisors of n of some other function. And so now we're going to talk about these summary type functions a bit more. And if a function f is multiplicative, well, then we define f of n to be the sum over all d that divides n, f of d, where we have a capital F for the summary function. And we claim that if f is multiplicative, then capital F, the summary function, is multiplicative too. And in fact, this is actually an if and only if, but we're going to need Möbius inversion in order to prove the converse. So right now we're just going to assume that lowercase f is multiplicative. And for multiplicativity, we remember we need to take two numbers m and n, so that the greatest common divisor of these two numbers is 1. And we want to find f of m times n, of course, capital F of n times n. Well, every natural number x, so that x divides m times n, has a unique factorization d times e, where d and e are natural numbers, so that d divides m and e divides n, and that is because m and n don't share any common factors. And so that means if I take f of m times f of n, well, that's the sum over all d that divide m, f of d, plus the sum over all d that divide n, f of e. And I can pull the sums out. I get f of d times f of e. Now these two don't have common divisors, so that means f of d times f of e is f of d times e, and the sum is just over all d that divide m and e dividing n. But if I already have them multiplied together, then when I sum over all d that divide m and all e that divide n, I'm basically just summing over all divisors of m times n, so this is the sum over all x dividing m times n, f of x, and that's capital F of m times n, and that's already it for this one. Another theorem here, and that is that sigma and tau are multiplicative, and yeah, that's because they are both these summative functions, right? Proof? Yeah, use f of n equals n and f of n equals 1 in the preceding theorem. Okay, so now we have a lemma, and we also, just like we did for the Euler-Phi function, we want to see if we can't compute these functions or find formulas. And so if p is a prime number and a is a positive integer, well then sigma of p to the a is the sum j equals 0 to a p to the j. It's the sum of all divisors, and that by the sum for geometric sequences is p to the a plus 1 minus 1 over p minus 1. The proof is basically right there, right? The divisors of p to the a are 1p, p squared, and so on, all the way to p to the a, and that means the sigma of p to the a is the sum from j equals 0 to a p to the j, and that's p to the a plus 1 minus 1 over p minus 1. That means that we can actually write down what these functions are with a product formula, namely, if we take the prime factorization of our number n to be the product pj to the aj, well then sigma of n will be product j equals 1 to s pj to the aj plus 1 minus 1 over pj minus 1, and tau of n will be the product j equals 1 to s aj plus 1, because, well, pj to the aj has aj plus 1 divisors. Proof? Quite simple. pi, pj have greatest common divisor 1 for I not equal to j, so that means that sigma of n is sigma of j equals 1 to s pj to the aj, which for multiplicative functions is the product j equals 1 to s sigma pj to the aj, and that's the product j equals 1 to s of the pj to the aj plus 1 minus 1 over pj minus 1. And for tau, we use the same argument, only that tau of p to the a is a plus 1, and that means this proof is done. Now we're going to talk about perfect numbers and Mersenne prime numbers. And so this is something that, again, goes way back to the ancient Greeks, but then Mersenne prime numbers are something that people are interested in because it pushes, again, the boundaries for primality testing. So a number is perfect if and only if it is the sum of its proper positive divisors. And that is the case if and only if sigma of n is equal to 2n, because n itself is also one of the divisors, right? And so now there is a theorem, and the theorem says that an even positive integer n is a perfect number if and only if it is 2 to the m minus 1 times 2 to the m minus 1, and verbally that doesn't sound like it's different, but in the first one the m minus 1 is in the exponent, right? Where m is an integer that is greater or equal than 2, because we have to make sure it's even, right? And we have to make sure, and so that 2 to the m minus 1 is prime. I'm going to say it later on also, but I might as well also say it here, and that is there also is a characterization for odd perfect numbers, but that one is beyond our reach right now. Okay, so what's the proof? Well, we look at numbers of the form 2 to the m minus 1 times j, where j is odd and m is greater or equal than 1. Well, sigma of j is greater or equal than j plus 1, with equality being true if and only if j is prime, right? Because if j is not prime, then we get more here, and if we get this exactly, then j must have been prime. And if j is prime, we get exactly this. Okay. Also, we want to note that sigma of n is equal to 2n if and only if, well, okay, we already knew that sigma of n is equal to 2n if and only if it's prime, so this is just perfect. And so this is just another way of saying that n is perfect, and that's the case if and only if we want to look at 2 to the m times j, which is sigma of n. That's 2 times 2 to the m minus 1 j, which is sigma of 2 to the m minus 1 times j, yeah. And we can break that up. That is sigma of 2 to the m minus 1 times sigma of j. And the sigma of 2 to the m minus 1 is just 2 to the m minus 1. We've just shown that on a preceding slide, so that's 2 to the m minus 1 times sigma of j. So that means n is perfect if and only if we have this equation here. And now for the direction right to left. So assuming that n is 2 to the m minus 1 times j being 2 to the m minus 1, we go right to left, and so for j equals 2 to the m minus 1 prime, we have that sigma of j is equal to 2 to the m, right? Because it's number plus 1. And that means that the equation holds, because now we have that j is 2 to the m minus 1, and we have sigma of j being 2 to the m, and that already means that even numbers of the given form really are perfect. Okay, now we have to prove the other direction, and for that we go to the next panel. And so for left to right, we have to take the equation that we had that said that the number is perfect if and only if this happens. Well, we now need to find consequences of this equation. And so if we're looking at 2 to the m times j equals 2 to the m minus 1 equals sigma of j, that implies that 2 to the m minus 1 divides j, because no odd number divides the power of 2. And 2 to the m divides sigma of j, because no power of 2 divides any divides an odd number, 2 to the m minus 1. Okay, so that means that j is 2 to the m minus 1 times some d, and sigma of j is 2 to the m times some e, and if we can just prove that d equals e equals 1, we ought to be okay. And so if we substitute into the equation up here, we get 2 to the m times 2 to the m minus 1 d, that's 2 to the m j, and that on the right, that's 2 to the m j, which is 2 to the m minus 1 sigma of j, and sigma of j was 2 to the m e, so this ends up being 2 to the m minus 1, 2 to the m times e, and we can see that we can cancel, and that means that we already have that d must be equal to e. So that means that j is equal to 2 to the m minus 1 d again, and we're now need to check what happens if d was greater than 1, and we're going to find the contradiction there, because what do we get? If d is greater than 1, we would have that 2 to the m times d is equal to sigma of j, and that would be yeah, that's because j is 2 to the m minus 1 times d, so we plug it in here and cancel the 2 to the m minus 1. So that would mean 2 to the m times d is sigma of j. Sigma of j is greater or equal than 2 to the m minus 1 times d, which is the number itself, plus the other two divisors that we know, 2 to the m minus 1 and d. And if we see that, we get a minus d plus d, so that goes away, so that's 2 to the m times d plus 2 to the m minus 1, and we can see that that can't work because we've just shown that 2 to the m times d is greater or equal than 2 to the m times d plus a non-negative number, and so that's not possible. So that means that d is 1, and that means that j is 2 to the m minus 1, and sigma of j is 2 to the m, which is j plus 1. And yeah, okay, so that's j plus 1 from here. Okay, so we now have that the numbers that n is of the right form, n is of the form 2 to the m times 2 to the m minus 1, and I felt like we were done, but remember the other thing that was said was that j was supposed to be prime. So if j was not prime, well then we would have that sigma of j is greater than j plus 1, but we had already seen here that sigma of j was 2 to the m, and so that means that j equals 2 to the m minus 1 is prime, and n really is all the way as indicated. Okay? And, well, if m is a positive integer and 2 to the m minus 1 is prime, then m must be prime. So because people were interested in these perfect numbers, people became interested in these factors that we must have. So a natural question to ask, given from the previous theorem, is that if 2 to the m is prime, what must m be? And, well, we can at least conclude that m must be prime, and that is, if m was actually a composite number with non-trivial factors p and q, then we would have that 2 to the m minus 1 is 2 to the p to the q minus 1, and that is 2 to the p minus 1 times sum j equals 0 to q minus 1, 2 to the p to the j, and that is the usual formula that you have when you take a power minus 1, then that is the base minus 1 times this kind of summation. And that would mean, of course, that that is composite, because p was greater than 1, and that handles this one. So definition, the number m sub m, which is just 2 to the m minus 1, so it's really not a terribly strange looking thing, but that thing is called the mth Mersenne number, in honor of a French mathematician named Mersenne, who probably not necessarily proved that one, but probably proved the theorem before that. Not quite sure, can't say that, I'm not a historian either. And if this number m sub m is prime, we will call it a Mersenne prime. The theorem up top here shows that not all Mersenne numbers are prime, but even when m is prime, m sub m need not be prime. For example, if we're looking at the number m sub 11, that's 2 to the 11 minus 1, and I know what that is. That's 2048 minus 1, so that's 2047. The part that I wouldn't necessarily know directly is that 2047 is 23 times 89, and let's see, how would that go? 2 times 89 is 160 is 178, so that would be 20 times 89 is 1780, plus 3 times 80, which is 240, would give us 2020, plus 3 times 9 is 27, giving us 2047. So these things can still be verified, and the more you train yourself to do reasonable arithmetic also in your head, the easier these kinds of things will be, and actually also the sharper your brain is overall, because actually we're now in the 17th or 18th presentation. I think I've recorded 17 right now, because I've skipped one, and I'm a lot sharper with numbers than I was as I started these things out. Okay, so let's talk about odd prime numbers. So if p is an odd prime number and d is a divisor of the Mersenne number m sub p equals 2 to the p minus 1, then we claim that for some positive integer k, we have that d is 2kp plus 1. So basically the divisors of Mersenne numbers that come from prime numbers, of course the one Mersenne number that comes from an even prime number is not that interesting, it's 3. So all the divisors of Mersenne numbers that Mersenne numbers that are natural candidates to be primes but aren't, must be of a very special form, namely they must be one of from a multiple of that exponent there. Okay, so the divisors must be there. Okay, so let q be a prime factor of this number m sub p equals 2 to the p minus 1. Well, by Fermat's little theorem, q itself divides 2 to the q minus 1 minus 1. Yeah, that's because 2 to the q minus 1 is equivalent to 1 modulo q. And so that means that the greatest common divisor of 2 to the p minus 1 and 2 to the q minus 1 is equal to q. And by an earlier result which we had, which talked about numbers that were of this form, power of 2 minus 1, the greatest common divisor of, if the greatest common divisor of two of these powers is greater than 1, then the greatest common divisor of the exponents must also be greater than 1. And because p is a prime number, that means that p divides q minus 1, and that means q minus 1 is m times p. And because q is odd, and that's because this thing doesn't have any even factors, we have that m is 2 times k for some k, and that means q is 2kp plus 1. And any divisor of m sub p is, of course, a product of prime divisors, and that means a really truly simple induction on the number of prime factors with multiplicity shows that any divisor of mp is of the form d equals 2kp plus 1, because anytime I take two numbers of this form and multiply them together, I get multiples of p plus a 1 at the end. Okay, so that was a quick overview of perfect numbers and where Mersenne prime numbers come from. And if you look at perfect numbers and don't consider them perfect, well, that is something that is, I would say, on one hand traditional, and again, for people who go naturally into number theory, it may really look that way for an outsider. The beauty is in the eye of the beholder, certainly. But it shows that Mersenne prime numbers have a place in number theory, and so there's a search for Mersenne prime numbers, and there is, in fact, an O of p cubed test for whether for a prime number p, the Mersenne number m sub p is prime. The search for Mersenne prime numbers has a really long history, and it's still ongoing. It's now using distributed computing, and if you're interested in that, go to mersenne.org. And it's really interesting, again, that here we run into these easy conjectures that are, in fact, easy to explain to people. It may not be as easy to explain to people why people are interested in Mersenne prime numbers, but you could tell somebody with basic knowledge of powers what a Mersenne prime is, and explain the conjecture is that there are infinitely many Mersenne prime numbers, but it's not been proved. And one motivation, one practical motivation then, or one historical motivation for looking for Mersenne primes is to search for even perfect numbers. Odd perfect numbers need to satisfy so many conditions that they would be very large and difficult if they exist at all. So apparently I wasn't quite truthful with you at the beginning. That's, again, I only play a number theorist on this show. I don't know whether odd perfect numbers are completely characterized, or if this just means that they found conditions and conditions and conditions, and that means that they have to be very large if they exist at all. And a proof that decides their existence or non-existence has not been found yet. Okay, so now we go to Möbius inversion, and that starts with the Möbius function, all named after the German mathematician Möbius, and I'm pretty sure that's also the one with the Möbius strip. And that Möbius function looks really strange, right? It's called mu, and it assigns to the number n equals 1 the value mu equals 1 equals 1. And for any product of r distinct prime numbers, it assigns the value mu of n equals -1 to the r. And to all other n, it assigns the value mu of n equals 0. And this is another one where I'm typically saying in class that no, mathematicians don't just fall out of bed and say, this is what I'm going to define. And as far as I could see from, as I prepared these slides, the motivation for why he would have been interested in this function comes probably from the last proof on these slides, where we prove that if the summative function is multiplicative, then the original function is multiplicative also. So first, we just prove a couple of results about the Möbius function, and one of them is that the Möbius function is multiplicative itself. Well, take two numbers whose greatest common divisor is 1. Well, then multiplicativity is trivial if 1 of m or n is 1, right? Because then the product is just the other number, and mu of 1 is 1 also, so nothing happens. If mu of m is 0 or mu of n is 0, there is a repeated prime factor in m or n, and that means there is also one of those in m times n, and so that means both sides are 0. So in this case, mu of mn is equal to 0, which is mu of m times mu of n. And if mu of m is not 0 and mu of n is not 0, well, then neither of the two numbers has a repeated prime factor, and hence neither does m times n, because remember we have that m times n greatest common divisor is 1. And then we just take Rm to be the number of prime factors of m and Rn to be the number of prime factors of n. And we know that mu of m times n is -1 to the Rm plus Rn, not times Rn. And we're back, and here's the plus. And that's, of course, simple algebra. That's -1 to the Rm times -1 to the Rn. And that is mu of m times mu of n. And that means that the Möbius function is multiplicative. Okay, the summary function, f of n, which is the sum over all divisors of n, mu of d, satisfies that the sum d divides n mu of d is 1 if n is equal to 1 and 0 if n is greater than 1. So we're basically just building up some facts about the Möbius function, similar to what we've done for the Euler-Phi function. It's just that for the Euler-Phi function we saw a little bit more motivation early on. And here's the proof. Well, we've got an earlier theorem that says that the summary function is multiplicative, and so that means we can concentrate on the prime factorization of n. So first note that for an exponent k and a prime number p, we have that f of p to the k is the sum over all divisors of p to the k mu of d, which is the sum j equals 0 to k mu to the mu of p to the j, and that's 1 because mu of 1 is 1. It's -1 because mu of p is -1 to the first, plus the sum j equals 2 to k mu of p to the j. Those guys are all 0, and 1 plus -1 is 0, so the whole thing is 0. And that means if this is the prime factorization of a number n greater than 1, well then f of n is f of this product, which is the product of the f of pj to the aj, and that is equal to 0 because no matter what I do, these exponents are all non-negative integers, and we get a product of zeros. All right. Now we are going to prove the Möbius inversion factor formula, and I think that is one of the prime motivations here, even though this will ultimately also be used for the last theorem on these slides, I think, and that is if you have an arithmetic function, and of this arithmetic function you know the summative function, the sum over all the d's that divide in f of d, then you can get the function back if you summarize over all the d divides in mu of d f of n over d, and that is true for all natural numbers n. Well, okay, so we just start on the right and see what happens. So this is the sum over all divisors of n, mu of d f of n over d, which is the sum over all d over n mu of d, and times the sum of over all e that divide n over d, f of e. And that's just the definition of the summative function. Alright, now we can certainly pull this out and turn it into a double sum of mu of d times f of e. But now we realize, okay, this is a sum where we first specify a divisor of n and then look at all the divisors e of n over d. We could have equally well specified a divisor e of n and then a divisor of n over e, and we would have ended up with the same product. Whether we choose the e first or the d first, both summations run over the same sets of pairs of numbers. And that means that this is the sum over all e divides n f of e times the sum of over all d divides n over e mu of d. And what we know from that, and here's where I'm using notation that is more familiar to people in probability theory, we had just proved in the previous lemma that this sum is equal to 1 exactly when e is equal to n, because this sum is only equal to 1 when d is equal to 1 here, and for all other greater d's, the sum, or this sum is equal to 0, unless, okay, tying up my tongue here. This sum is equal to 0 when n divided by e is not 1, and that means this sum is only not non-zero when e is equal to n, and at that point in time it's exactly 1. And so that means this is a sum over all e divides n f of e, and the only summand that doesn't have a 0 factor is e equals n, and so that means that we get f of n at the end here. Okay, and that should now give us that if you have an arithmetic function and you let f of n be this summative function over all divisors of n f of d, and if this summative function is multiplicative, then so is the function that we were summing. So that is the converse of something that we proved near the end of the Euler phi function section. Proof? Well, to prove that something is multiplicative, we need two numbers m and n that have greatest common divisor 1. Then f of m times n is, from the previous formula, it's the sum over all divisors of m times n, mu of d, f of mn over d. And that is the sum over all divisors of m and all divisors of n, which we call dm and dn. Mu of dm dn, f of m over dmn over dn. So we're just splitting that up. And now we use that f as well as mu are multiplicative, so this is still the sum over all the dm's and dn's, mu of dm, mu of dn, f of m over dm, f of n over dn, and we're always using here, of course, that dm and dn as well as these two fractions have greatest common divisor 1. And now we can just factor stuff out. This is the sum over all the dm divides m, mu of dm, f of m over dm, sum dn divides n, mu of dn, f of n over dn, and that's f of m times f of n, and that is the end of this proof. Okay, I jumped over it a little bit quickly, and to be perfectly honest, that is because I was very happy that I got through the proof of the Möbius inversion formula. But if you analyze the proof of the Möbius inversion formula, you basically see that if you want to get a formula that expresses the function lowercase f in terms of the summative function capital F, then that computation, if you just throw in an arbitrary factor mu there, that computation shows the properties that the function mu would have to have, and that probably, hopefully, or if not, then he had some other brilliant idea, but that is the kind of thing that can lead mathematicians to define auxiliary functions such as the Möbius function, which offhand, when you first look at them, look a little bit strange, because if you just stick out the definition, they look like they come out of nowhere. Of course, the alternative would be to first start the proof and then say that, well, we need something that looks like such and such, and either approach is equally hard to understand, I think. Mathematics at this level just has a certain intrinsic difficulty. One of the things that you probably want to do is go back, look at the proof of the Möbius inversion formula, and figure out for yourself how that proof really informs the definition for the Möbius function. Other than that, you've got some homework to do. I've got a class to teach in 45 minutes, and so I'll see you later. Bye.